This is our preliminary design plan for the Highway Indigenous Food Sovereignty Garden.
The aim of this project is to design a stormwater management plan and renewable energy system. The stated aim for this project is to restore the land to its natural state, garden vegetables and plant-based medicines, and plant forests without the use of fossil fuels. In line with these goals, the client wants the following: a stormwater management plan, including the design of retention pond and water distribution system to manage drought conditions, and to replace an existing well. A renewable energy system, preferably solar, making use of an existing structure on the property, as well as any electrified components of the water distribution system. Because of the budgetary and time constraints of the project, a maximum of 4 months from initiation to completion and a budget of approximately $5,000, the design team has limited the scope of the project to the feasibility study, design, and pricing of both systems. The next thing I'll be talking about is the schedule that the team has made for the project, and it is expected to commit 7 to 9 hours to the course weekly. The team's weekly schedule will be aimed to ensure that all due dates are met and every deliverable is completed in a timely manner, with Monday being time for a project manager meeting, and Tuesdays and Wednesdays is a team meeting to work out all of the plans for the week. Thursdays are for individual time to get everything completed. Fridays is a check-in meeting. Saturday and Sunday is time to finish the deliverable and edit. So thirdly, I'll be talking about the weather conditions in Kingston. And this is a critical part for our design plan because without it, it'd be very hard to calculate the water distribution. And on the screen, I have 3 charts here showing the temperature, the wind, and the precipitation per year in Kingston. So the average temperature in Kingston is around 8.4 degrees, with precipitation being about 1,102 millimeters. And the average hourly wind speed in Kingston experiences seasonal variation over the course of the year, with windier parts of the year lasting for 5 months, with average wind speeds of more than 12.4 kilometers per hour. And this is helpful because without this information, it'd be really hard to make our plan, like I stated earlier. So wind has a drying effect, and this can cause wet plants to dry faster, reducing disease chances. However, it can also remove water faster than the plant can replace it. And this can be a problem in the summer when combined with high temperatures and low soil moisture. And with excess wind, there can be considerable damage to the plant, and this can be prevented by hedges, which can also break the sound and increase biodiversity to the land.
Water collection. Since there are few structures on the property with roofs that can redirect the flow of rainwater to a collection system, another method has been considered. So instead of using rain barrels or totes to collect the water, water would primarily be collected using a land surface collection system. So we're proposing a sustainable urban drainage system, which allows for a larger water catchment area and the possibility to inspire a miniature wetlands ecosystem within and around the catchment area. Rain barrels and totes can still be used alongside the new SUDS design. And since the water will be collected in the ground, filters will need to be implemented to remove any dirt that may get into the collected water. Though you will see multiple designs, the general premise of our design is that the water will be collected and then transported via a solar-powered pump or a dry hydrant to a storage tank.
So this section deals with 2 proposed designs for a water collection system. One of the design challenges we faced was finding a suitable water collection system given the site and water requirements, because generally most modern rainwater harvesting systems employ rooftops as catchment areas. However, since the water is mainly for irrigation purposes and the other suitable site on the property will not be able to house any gutters or anything like that because of the planned solar panels, we figured that a ground-based system will suffice. And there are several sort of methods of creating a ground-based catchment area. But we have found 2 designs which we think are adequate. So the 2 proposed designs are a retention pond and a constructed wetland. What you see before you is a retention pond. And that is exactly as it sounds. It is a permanent pond that acts as a storage basin. And what this would involve in terms of construction would be excavation, as well as the installation of sort of a geomembrane or plastic liner to prevent groundwater infiltration. So some advantages of this design are that it would be extremely cost effective. It's the cheapest option of the 2, and it promotes biodiversity in the surrounding area, provided that there's proper land management. And this is sort of the best practice, industry best practice in terms of agriculture. You see these sorts of retention ponds usually in agricultural settings, and given that it will be a bit larger and provided that the water quality is suitable, it could potentially be used for recreational purposes. But some disadvantages of this is that it does require maintenance, regular maintenance, which would involve inspections for the accumulation of sediment, organic debris, weed growth, that sort of thing. But if it's not maintained properly, having a permanent open pool of stagnant water could lead to issues such as algae blooms, as well as mosquitoes and odors and whatnot. And looking at the maps that we were provided of the property, we'll have to consider where we build it, because these sorts of things are generally restricted to areas with shallow slopes. And as well as the fact that the liner could be expensive. And these are generally considered to be less effective than constructed wetlands in removing pathogens from the water. And I will talk about constructed wetlands now. So we're proposing a constructed wetland, which it has the advantage in that rather than just storing water, it actually tries to mimic the natural water cycle, how water flows through natural habitats. And there are many advantages to this, and constructed wetlands are considered to be extremely effective natural filters, and they're very efficient in the removal of pathogens and dissolved nutrients. So the installation of a constructed wetland would be very similar to a retention pond, except what we would propose is that in terms of water storage, there could be a subsurface water tank where water is transported to after it's been quote unquote treated by the wetland, which could be retrieved by pumps mentioned in the previous section. So this is the more expensive option, but there are advantages. The main being that it significantly outperforms other methods of water control in terms of the removal of pollutants and filtration abilities. And it is supporting and working with the local ecosystem, which is a big point. And I think it sort of falls in line with the philosophy of the project here. However, once again, an issue with this is that we're limited to sort of flat land. So we'll have to take a look at the property, see what we can actually implement. And these sort of created natural systems come along with all the associated maintenance issues, such as mosquitoes and algae bloom and whatnot. And the maintenance for a constructed wetland is typically more intensive than a retention pond. However, benefits of that increased maintenance is that you are able to, for example, when weeds die in the winter, you're able to harvest that for fertilizer. So there are added benefits. It's sort of like adding another farming system to your project. And while for this section we don't have specific figures for the cost, the water collection system we believe will end up being one of the most expensive parts of the project, mainly because of the excavation and landscaping that needs to be done.
Water distribution. Water can be distributed in different ways based on the different purposes it needs to serve. From the storage tank, water is pumped, again, using a preferably solar-powered pump, so it can be transported to hoses or sprinklers or faucets. And then for the barrels and totes closer to the smaller plants and herbs, spouts at the bottom of the barrels can be connected to pipes. So these pipes would run alongside the plant beds and they would have holes cut in them, as you can see from the top pictures. And this serves as a hands-free way to deliver water to the plants. For these barrels, pumps aren't needed as gravity would provide the necessary water pressure. And again, filters will be placed between the faucet and the pipes to remove any sediments that get into the barrels. And this can be seen in the bottom picture. I also wanted to touch on the water requirements, as this will be a number that we use in our designs and feature calculations. So because of the wide variety of plant species on the property, the variability in their needs, and the general imprecise nature of watering plants, the weekly water requirements were estimated based on the most popular plants on the property, which we got from the spreadsheet that was provided for us. So using information gathered from online sources, the estimated water requirement was calculated to be about 4,800 liters of water per week.
Since it has been decided that solar power will be the method of electricity generations, it's important to look at the variety of solar panel models available. The models available fall under monocrystalline, polycrystalline, and a hybrid of the two. Monocrystalline is more expensive and more energy efficient, while polycrystalline is the more affordable and less energy efficient option. However, there's hybrid models that allow for a good median between energy efficiency and affordability. A good choice of this is the HiQ powered dual cell hybrid model, and each panel of this produces about 330 to 460 watts. Based on surface area calculations, each wooden structure can ideally hold 6 of these solar panels, which sums to a weight about 240 pounds the structure would need to hold. The average cost of a solar panel system in Ontario is $234 to $259 per watt. While it is still yet to be determined the exact electricity needs, it was found that 5 solar panels are needed for a 100-watt water pump, and approximately 15 solar panels are needed to power a small house. So it is safe to predict that the number of solar panels needed will lie within this range. Estimating that approximately 6 solar panels are needed, the cost can be estimated to be approximately $4,600 for a 330-watt hybrid solar panel system.
Our testing plan includes mostly mathematical models. For example, the sample calculation equation will be used to test once our design is more defined if the system will be able to meet the water collection requirements. So this is our risk analysis. Time constraints and major scope changes fall low on likelihood of occurring and the impact of occurs. Unavailable information and team skills fall higher on likelihood of occurring and on low impact. Most team members don't have much background knowledge on solar power or technical components of water collection and distribution system, but research can and has been done to solve that problem. As far as unavailable information, estimates can be made based off of research as well. Our most likely and biggest impact risk is the budget constraint. So, the design will most likely go over budget. The possible solution to this is getting other funding by asking for donations and collaborating with other organizations. We are currently in the process of reaching out to other groups and organizations about this.